Alright, so here we go. Welcome back to Curiosity Dude's channel. Today we're diving into how we became smart little critters and how our brains evolved. But wait, it's not just about brain evolution. It's also about how this evolution is linked to our diet. So, don't forget to like this video and subscribe to the channel. We got plenty of interesting podcasts coming your way. Evolution has a way of simplifying things. What's important evolves faster, and once it reaches an ideal state, it doesn't change much. Our diet and brain evolution showcase this perfectly. Back when we were tiny creatures scampering around in the late Mesozoic and early Cenozoic eras, we were mainly insectivorous. To be precise, we were pretty much omnivorous. Purgatorius, the first primatomorphs, were the most omnivorous mammals of their time. Most mammals back then, with few exceptions, were almost exclusively insectivorous, which makes sense. If you're a small creature living even in a tropical climate, you'll be insectivorous because when it gets a bit cooler at night, what else can you do? If you're small, you lose heat quickly, especially if you're cold-blooded, so you need to replenish your energy losses by eating at night. To get as many calories as possible in a short amount of time from small bites, because hey, you're tiny, so big meals are out of the question. You'd have to munch on insects. What other source of calories could you find? So, munch away on bugs. It's a smorgasbord out there, especially with the emergence of social insects like termites, ants, and bees during the Jurassic-Cretaceous transition. Our Purgatorius ancestors, those early primatomorphs, were savvy little guys. They chomped on insects and fruits. This dual diet was a game-changer. Sure, there were other plant-eating mammals like condylarths leaning toward herbivory, but most ended up as hoofed animals. Our tree-dwelling ancestors, though, could munch on fruits as well, which were already flourishing by the end of the Mesozoic. Leaves, while not the most nutritious option, were also on the menu in the tropics, where you could find a fatty leaf, resin, nectar, or even bird eggs. Basically, if it existed and was edible, they ate it. But insects were the most crucial part of the diet, and to catch those bugs, you had to stay agile. And there you have it, a reason for brain evolution. When you're hopping from branch to branch, you need to measure your jumps accurately to avoid a disastrous fall. Our ancestors were pretty good at this leaping business. And hunting insects? Well, insects come in all shapes and sizes. Imagine a grasshopper. Let's say a 5 centimeters grasshopper facing off against our 6 to 10 centimeters ancestor Purgatorius. That grasshopper must have seemed like a formidable beast. Even today, a regular old grasshopper can give you a nasty bite if it gets the chance. So, hunting insects was a small but vital incentive to get smarter. And then, of course, our ancestors didn't just eat insects. They ate fruits, leaves, and whatever else they could find. That was the first spark, the initial stage of brain evolution. As time went on, throughout the Paleocene, and at least the first half of the Eocene, our ancestors grew in size and became increasingly active climbers. With this growth came several changes. As they grew and became more agile, their grip strengthened, and they developed opposable thumbs on their hands and feet, perfect for grasping branches. These changes in their physical form led to changes in their brains as well. When they were small and lived in dense foliage and forest floors, their primary sense was smell. Next up were those whiskers. Our ancestors had well-developed whiskers, evident from the small holes in their skulls where blood vessels fed these sensory hairs. But as they grew bigger and more agile, smell and touch, via whiskers, became less important. When hopping from branch to branch, whiskers didn't really touch much, and scents were all around but less directional. Thus, vision took the lead, smell declined, and the brain's front part shrank while the back part expanded, improving their jumping skills. The cerebellum grew, evident from brain molds of late plesiadapiforms and early adapiforms. Their brain shape changed. from an elongated brain to a triangular one with a narrow front and wide back. Chewing muscles, initially attached along the brain case, moved to the front. With growing plant food intake, their jaws evolved for vertical strong bites. Insect-eating ancestors had pincer-like jaws to catch and crush insects with sharp teeth. Now, with more fruits and nuts, jaw strength increased. Jaws, once like pincers, became like nutcrackers, shorter faces, stronger vertical muscles, and a more compact structure. Monkeys and apes, unlike lemurs with dog-like snouts, evolved shorter faces, reflecting these changes. Our jaws got shorter and higher, altering our forehead configuration. The forehead shortened and narrowed as the olfactory parts of the brain shrank, while chewing muscles moved to the front. This caused the so-called post-orbital constriction, less visible in modern humans but prominent back then. The back of the brain case freed up from chewing muscle pressure, allowing it to grow more, and skull sutures stayed open longer. This late fusion of skull sutures is a unique human trait. Human skulls consist of separate bones with sutures that can grow until they fuse in our 20s and fully fuse by 55 or even 80 years old. But earlier ancestors had sutures that closed much later, allowing the brain case to grow. In strepsirrhines, the metopic suture between the frontal bones remains unfused longer due to their reliance on smell. But as our ancestors' sense of smell declined, the metopic suture fused sooner, reflecting another quirky turn in our evolutionary tale. Strange but fascinating, isn't it? All right, let's wrap it up with a fun spin. So, as the back of our skulls grew, the parts we now flaunt as humans, like our sense of smell, actually shrank. This shrinkage made room for the rear of our brains to expand, leading to a sort of evolutionary leap forward. About 50 to 40 million years ago, our ancestors experienced significant changes. Those strong chewing muscles moved to the front, the back of the skull grew, visual and motor parts like the cerebellum got bigger, and the tactile sensitivity of our hands increased. The brain's parietal lobe started linking different senses, leading to a more integrated perception. Fast forward, and we got bigger, crossing the 500-gram threshold, a crucial divide between small, night-dwelling insectivores and larger, day-active creatures. Larger size meant less reliance on insects for food. Fruits and leaves became mainstays. This switch to a fruit-rich diet lasted from about 45 to 40 million years ago until more recent times. Around 28 to 27 million years ago, actual apes emerged, growing larger. Interestingly, our brains evolved sluggishly along the way. Crazy, right? Evolution's got more plot twists than a soap opera. So, here's the kicker. Different systems in our bodies evolved at different speeds. Teeth and jaws evolved first because eating is sacred. That's priority number one. Then came hands and feet because movement matters, either to get to food or to flee from danger. Early plesiadapiforms had brains like modern insectivores, which makes sense. Early narrow-nosed monkeys like Australopithecus had cat-sized brains that structurally resembled lemur brains, despite looking more like monkeys. Their olfactory bulbs were still quite developed compared to us, though. When it comes to early hominoids, we see their brains were primitive, similar to early narrow-nosed monkeys. They had human-like teeth and somewhat human-like hands and feet, but their brains were still simple, narrow, small frontal lobes about 130 grams. Even with such modest brains, they thrived. Evolution, it's full of wild rides, isn't it? And then enters the wild card, sociality. Early primates weren't the sharpest tools in the shed, so their social structures were pretty basic. But for more advanced monkeys and apes, social interaction drove brain evolution. Our brains evolved for communication, essential for cooperation, avoiding danger, and gathering food. This brain evolution continued until the early Australopithecines. Their brains, around 130 grams, grew to 300 to 400 grams, still small compared to modern human brains. Australopithecines, with brains akin to modern chimps, had similar tasks. Their occipital lobes grew as they ventured into the savanna. Their frontal lobes developed a bit more since their hands were free for various tasks, even if they hadn't mastered tools yet. They likely used sticks and stones and foraged roots and berries. So, while their brains didn't change drastically, their social structures and tool use started setting the stage for further evolution. Evolution's got more plot twists than a soap opera, right? The real breakthrough happened between 2.5 and 2 million years ago, or even up to 1.5 million years ago. It wasn't an overnight switch, but a gradual process marking the transition from Australopithecus to early Homo. Interestingly, the usual evolutionary sequence of teeth first, then limbs, then brains flipped here. Brains took the lead while teeth and limbs stayed relatively unchanged. Around 2.5 million years ago, our ancestors started to lean towards a meat-eating diet. This wasn't immediate, but happened over a long period. Thankfully, we didn't become full-blown predators, but our diet shifted significantly in that direction. Evolution loves to keep things interesting. So, what really went down during this time? There was this big shift to savannas, which transformed thorny bushes into open grasslands. Suddenly, powerful competitors emerged, like mega-herbivore pigs, similar to modern warthogs but bigger, and baboons, our primate cousins who evolved in the same African savannas under the same conditions. Baboons had a head start because they didn't have to transition from four-legged to two-legged movement, saving evolutionary time. While we spent 3 million years getting upright, baboons reached their peak 3 to 2.5 million years ago. Fossil Therapithecus baboons were giants, weighing around 100 kilograms and standing tall. Modern baboons are impressive, but these guys were even more so. They were strictly plant eaters, a rare trait for primates, but they made it work. Fascinating how these evolutionary dynamics play out, right? Yes. Those gnarly rivals with their powerful jaws and big old canines. Baboons, for instance, were formidable competitors. They were social, banding together for protection, and they were definitely not to be messed with. They outpaced our ancestors, the Australopithecines, leading to a massive die-off among them. Only a few species like the South African cerebellum and Australopithecus garhi hung on. Around this time, the climate shift towards more open savannas led to the extinction of many large herbivores that once thrived in dense thickets. Giant buffalo, hippos, rhinos, elephants, short-necked giraffes, and other megafauna either perished or adapted in ingenious ways. Giraffes, for example, evolved their long necks to reach tree canopies, and some buffalo moved into the shadows. As the herbivores dwindled, so did the predators. The whole ecosystem was reshaping itself, and our ancestors had to adapt quickly or face extinction themselves. Evolution sure doesn't play favorites, huh? Exactly. As the megafauna and large predators dwindled, the predator lineup in Africa got pretty sparse. We're left with a handful of big predators: lions, leopards, and not-so-large cheetahs. Hyenas, though sizable, aren't the top dogs. African wild dogs are fierce, but not large. And then you've got jackals and wolves, which aren't all that intimidating. Bears vanished from Africa at this time, too. With fewer predators, lions specialized in hunting zebras, antelopes, and wildebeest. Leopards stalked gazelles, and cheetahs chased down their prey with mad speed. Hyenas and the like scavenged what they could. Around 2.5 million years ago, this created an open niche for medium-sized predators. Cue our ancestors. These early hominins transitioning from Australopithecines to early Homo jumped into this new niche. Evolution's twists and turns sure keep things interesting, don't they? Right now, Our ancestors were in a bit of a transitional phase. The shift to a meatier diet, thanks to our omnivorous, insect-eating past, led to significant changes. Meat, lacking plant cell walls, is easier to chew and provides more calories. So, less chewing meant more energy with less effort, pretty handy. This diet shift favored individuals with smaller jaws. Smaller jaws weren't necessarily better, but they were no longer a disadvantage. Chewing muscles were the first to change. Skulls show this through the reduced attachment points for these muscles. Australopithecines had large crests, while early Homo species had smaller, more human-like skulls. Jaws remained relatively large, but teeth began to shrink. With less energy spent on chewing, brain size started to increase rapidly. Evolution really threw a curveball here. Exactly. Catching meat was way tougher than munching on grass. Grass just grows there, but meat fights back, literally. You have to outsmart it. This challenge led to the development of early language signs, as hunting required coordination and communication. Our ancestors, not being natural predators, had to invent tools. Around 2.6 million years ago, the first tools with sharp edges appeared, clearly made for butchering meat. Making tools was tricky and needed brain power. Those who could make and use tools effectively gained an evolutionary advantage. As they relied more on meat, chewing muscles decreased, as seen from the skulls. Reduced jaws meant less chewing, but more thinking. Brains started to grow quickly, as smaller jaws were no longer a disadvantage. One thing led to another, and before you know it, brains were booming and jaws were shrinking. Evolution at its finest. And there it is, we crossed the so-called brain Rubicon. This refers to a brain size of about 800 to 900 grams, sometimes considered as low as 700 grams. It marks the crucial boundary where smaller brains can't support tool-making and complex thought, while larger brains can. Early Homo species between 2.5 to 1.5 million years ago hovered around this brain Rubicon. Homo rudolfensis had big jaws and teeth, but weaker muscles. Then came Homo habilis with smaller jaws and teeth and less muscular strength. Their brains just kept growing. At around 700 to 900 grams, brains could handle basic survival tasks like foraging. But we didn't stop there. We weren't specialized hunters, so our brains continued to grow and develop. Evolution is wild, isn't it? All right, so here's the scoop. We were omnivores, making tools and competing with each other. Different human species like Paranthropus and Australopithecus were around. Those with beneficial mutations, bigger brains, thrived because they could better care for their offspring, passing on these brainy genes. Less fortunate, less intelligent ones didn't make it. As a result, brains grew rapidly until about 25,000 years ago when they started to shrink. But that's a tale for another time. Brain evolution was closely tied to our diet, and vice versa. So, eat well, think about what you eat, and you'll be just fine. Don't forget to subscribe to the channel, join the Telegram channel, leave comments, and share your thoughts. There are undoubtedly more factors at play, and your version might be just as interesting. Like, dislike, whatever you feel. Just engage. Cheers, and until next time.